Yeah.
Okay, folks, welcome back to our evening session. We only have one talk today. It's by Gleb Aminov from Stony Brook, and he will be talking about Dell systems and the Seiberg-Witten prepotentials.
Yeah, thank you very much for giving me the opportunity to speak here. So please ask any questions if you have them. We have like 10 people approximately, so we should be able to discuss more. Basically, this is the review of some older results, and like so I'll try to be cover a bit more than I would cover if it was like some talk about some particular result or new result. So I'll just try to go through the beginnings a bit, and from how the Dell systems were introduced, and to some results concerning particular representation for the Dell Hamiltonians. So the plan goes as follows. I would like to start with just some origins in classical PQ duality and how the two-particle double-elliptic system was introduced. Then I will show the construction by Mironov and Morozov that involves higher genus theta functions, and I also show another construction by Braden and Hollowood. These are the older constructions, and I'm not going to show the formulas which recently were derived in a quantum case by Peter, Shamil, and even more recently by Zotov and Grekov and others. So then having the Mironov-Morozov construction, since it's like the Poisson commutativity is a conjecture, the first steps were to try to figure out how to prove the commutativity, and so some first steps I was interested in doing were eventually finding the necessary conditions for the commutativity. So we were able to find some Theta-constant equations that can be regarded as necessary conditions, and this eventually gives what we call Theta-constant representation for this particular Seiberg-Witten curves, and also some nonlinear equations, which are generalizations of WDVV equations, because there is a problem if we are working with elliptic systems, namely we are working elliptic Calogera, elliptic Regenars, and or Dell system. WDV equations, they are not they don't contain they're not useful because the determinants are zero due to the properties of the period matrix. So there should be some analogs of WDV equations, and we present our equations that are not as straightforward. Maybe they involve some higher genus theta constants, but nevertheless they do the same trick. They allow you to compute the prepotentials, and they also involve third derivatives of the prepotentials as WDV equations. And finally, using these equations, you can compute the corresponding Dell prepotential, which is supposed to be the low energy effective action for the 6-dimensional 2,0 star super young Mills, I think, right, Peter? And I just call it for simplicity double-elliptic systems. There's also the whole picture with involving like brain constructions. I'm not gonna be able to talk about it much. So in this talk, I will be just showing a lot of formulas, and there will be more mathematics and formulas than physics and brains. But you can also talk about brains and M theory, because our like integrable systems and spectral curve arise when you consider M5 brain, at least in these systems I'm going to talk about today. So let's move on. Some incomplete list of references here, just the bare minimum. Obviously, the origins of PQ duality are from Rugenars, and the first papers on double-elliptic systems, and some Seiberg-Witten papers on prepotentials. So let's start with classical PQ duality, which is the action angle transformation for Collier-Rugenars type systems, and just naively speaking, they interchange the types of dependence of P and Q coordinates. So if you have a self-dual system like a rational Collier, you have rational dependence in momenta and coordinates. This means that eventually the system is going to be self-dual, and there is explicit coordinate transformation for each of these examples here. And so trigonometric algebra is dual to rational Rugenars, and trigonometric Rugenars is self-dual again, because both dependencies in momenta and in coordinates are trigonometric. So this is the classical picture. So the next question, Braden, Marshakov, Mironov, and Morozov, they tried to do the same for elliptic systems, and for n equals 2 they actually succeeded, and they also have explicit coordinate transformations, and they derived this answers for dual systems and explicitly self-dual system for two particles. And the main feature here that they noticed is that the dependence in the elliptic Jacobi function is actually coordinate dependent. So the modulus this k in the Jacobi function is coordinate dependent. This led to two different constructions for higher particle, for many particle case, and so we will discuss. We'll mostly focus on Mironov-Morozov construction, which takes these elliptic functions and suggests some higher genus theta functions to be building blocks for Hamiltonians. And Braden and Hollowood, they took more geometrical approach, and they introduced the spectral curve, also in terms of higher genus theta function, but it's slightly different. So I will focus on Mironov-Morozov approach today. And actually the relation between these two Hamiltonians, I think, is still, we are still in progress of understanding. As far as I understand, Peter and Shamil, they quantized the Braden and Hollowood, the Hamiltonians, or like their Hamiltonians are closer to Braden and Hollowood, and the quantization of Mironov-Morozov Hamiltonians is not done yet. So, but there is definitely
for n equals 2, they're the same, right? So
yeah, for n equals 2, that's yes. As I said, that for n equals 2, this is undisputed. Everything works here. Everything is explicit. For many particle systems, there are no explicit coordinate transformation, and this creates a problem that we don't actually know what is better, or how to, like, maybe both constructions could be related, and actually everyone thinks now that they should be related, but we don't know exactly how yet. So before I move on and introduce the construction, obviously we need higher genus theta functions, and they're defined with the help of the period matrix. I'm not at the period matrix is obviously the integrals over differentials on the Riemann surfaces. I skipped this slide here, and it's like supposed to be in for g equals 1. This is just the module, the tau. You have 1. It's not a matrix, it's just a complex variable, but for higher genus you have the whole matrix, and the definition is close to genus 1. So you have the matrix multiplied by this both sides by the vectors from like n is a integer vector, and it could be and shifts are considered to be some rational vectors. So if alpha or beta are integers, they don't do much. This stays the same. But if alpha and beta are some rational vectors or vectors with rational entries, then this actually changes the theta function, and this is called theta function with characteristics. So yeah, alternatively, the theta function can be defined with through its quasi-periodic properties. It's like the properties so that if you shift z by some integer vector m, the function should be multiplied by this exponent, and if you shift z by some omega times m, then you should see this another exponent which also includes the argument z. So this is a pretty this is not a hard exercise to start with this properties, introduce the Fourier expansion, and derive this formula up to some constants. So the construction of Mironov-Morozov suggests to use this ratio as the Hamiltonians of double-elliptic systems, and this comes from the fact that in n equals 2 we had the modulus depending on flat moduli A's in the Seiberg-Witten theory. So they decided to construct some ratios of theta functions where the period matrix is the period matrix of the corresponding Seiberg-Witten prepotential, and this is just the second derivative of the Seiberg-Witten prepotential. And the Poisson commutativity is assumed under this canonical symplectic structure. So z's are actually the vector z. As you can see, the vector has n components. So it's like we have n momenta. Z1 to Zn are the coordinate particle momenta. And the period matrix is actually dependent only on the flat moduli and some parameters, and there is no z dependence in the period matrix. So to test this, you need to know the prepotential of the corresponding spectral curve, and this is partly why this statement is still a hypothesis, is that you actually don't have the full analytic expressions for the prepotentials. You have full analytic expressions for the Nekrasov partition functions, but you need to take some involved and some complicated limits, and you don't have nice analytic expressions for the prepotentials. So, and also I'll mention briefly the construction by Braden and Hollowood. So they suggest that the curve is actually of genus n+1, and that this is schematically is the spectral curve equation. So I won't go into details of of this. I would have, but I don't think I have time. So the construction is a bit different, and if you try to write it in the same form, then the period matrix will be simpler, I think. So it's not going to be real. So their construction is not related to the derivative of the prepotential. So you don't need to know the prepotential to work with their Hamiltonians. So it's, in this sense, it's simpler. And yeah, that's why the, yes?
Yeah, so the just to make sure I follow the from the symplectic form, not before. You're saying that the Coulomb waves AI, they are the coordinates, right? So like AI and ZI are canonically conjugated.
Yeah, I will rewrite this the Poisson commutativity conditions, but it's just, yeah, you have momenta as a arguments of the theta function from P1 to Pn or Z. So Z and P are the same. Z are the momenta, and T is only dependent on the flat modular.
These are momenta and coordinates are the A's, right?
Yeah, yes. So normally you would like A's are usually action variables. So this is probably the formulation in terms of the action variables.
Okay, I see. Right. So
it's not really coordinates. To get coordinates, you need to rewrite A's somehow. So this is
okay. Good. Got it. Yeah.
But from the point of view of the commutativity or Poisson commutativity, we just need to know that T is only a function of A's and Z's are separate here.
The thing that puzzles me is that the AIs, they're not gauge invariant, right? So there's a wild symmetry that acts in them. So
yeah, T is only a function of the this construction is particular for AN, for S or SUN. So there's only differences. T is only a function of differences of AA minus.
Okay, yeah. So it's manifestly wild invariant if you write it down.
Yes. And all the formulas, and I will be writing down. Yeah, this is what we use from the start. We just assume that it's only a function of differences. It comes from the fact that, yeah, there's another property that we also implicitly use that says basically that it's only a function of differences. And if you drop this assumption, maybe there's more general facts to say, but we didn't explore into this. The first thing to do is that in order for this Hamiltonians to commute, there should be some non-trivial identities or constraints. So in order to see this, we can write the Poisson brackets between Z and T as some functions of T again. So in general, these are the third P, I, J, K. If you just use the symplectic form, this is just the third derivatives of the prepotential. So they are again functions of AIs. But if you imagine that you can go back from the function of i's back to the function dependence on T, you can assume that you can write some kind of bracket that is written in terms of Z and T, and you are not actually thinking about A dependence, and you can actually forget the prepotential and try to figure out what are the consequences of this kind of a bracket. Obviously, this bracket will be not symplectic, or there will be some peculiarities, but it's nonetheless it's still gives us non-trivial constraints. And what I mean by the constraints is that now, if you apply this bracket and just write down the commutation relations between two Hamiltonians, A and B, you see that you are summing up functions of Z, which are in this bracket. Every derivative of a Hamiltonian is a function of Z, and you're summing up these functions of Z with some constant coefficients p, which are only functions of the period matrix, and they don't depend on z. So this statement says that, as we will show later, whatever you have in these brackets here could be thought of as a some weight 3 theta function. So it's a linear space. So whatever we have here is vector in some linear space, and we are summing up these vectors with some constant coefficients and asking asking for non-trivial solutions in this coefficient. So basically saying that some array of vectors is linearly dependent, and this creates a constraint. And actually, for 3 and 4 particles, we see that this is actually these equations are actually theta function identities. So these vectors will be, for any period matrix, these vectors will be linearly dependent. But for higher number of particles, we'll see that actually it's not going to be an identity. It's going to provide us with some non-trivial constraints. So this reminds us immediately of something called the Schottky problem, where people look for constraint on the period matrices, because if the basic fact is that for compact Riemann surfaces, the modular space is just a linear in genus. It's like 3g minus 3 for g greater than 1. So, but if you consider exactly like we do here, if you try to go to just the period matrix and consider and look at each matrix element as a moduli, you'll find out is that there's more. It's like grows like g squared, and so for g greater than 3, there should be some constraints on the matrix elements. Otherwise, you have more. Otherwise you're saying that the dimension of the modular space is bigger than it actually is. So this creates for genus equals 4, this creates a Schottky constraint, which in general can be written like this. So this is the first constraint, and if you compute actually for g equal 4, number of elements in the period matrix is 10, right? 5 times 2, and you should have only 9, right? 3 times 4 minus 3. There is only 9-dimensional moduli space. So you need one constraint, and this one constraint can be written with help of Theta-constant like this. So this is exactly the constraint. So this reminds us the situation with what we have for the commutativity conditions, that we start with some identities. Here we also we don't need any constraint for for genus equals 1, 2, 3, and then you encounter constraints in higher genuses. So let's dive into this in more detail, since we are talking here mostly about elliptic systems, and I think I will be able to present a bit more explicit formulas, and maybe people won't be scared too much, because here everyone works with elliptic functions at some level. So let's try to write down some explicit constraints that we can get from this necessary condition. So rewriting, as I said, this bracket can be rewritten as some in terms of the linear space of weight 3 theta functions. So it's actually a vector, and I call this vector like C alpha. And so we sum up vectors with constant coefficients, and this means that actually the matrix constructed of C alpha vectors should be of the rank should not be bigger than something, because this matrix is not actually in general, it's not square matrix, but we'll eventually come to the determinant. So there should be some minors or some determinants should be 0 in order for this to be true. So, and the hypothesis here, or the statement, is that this constraint provides some information about the possible Seiberg-Witten curves we can encounter, and basically we're saying if we start with these Hamiltonians, we will only get this kind of systems, integrable systems, and we will basically see that we are working with a family of integrable systems, and we'll be able to figure out what family it is just by taking the general form of the Hamiltonians without any without concrete knowledge about the prepotential, and then we'll be able to figure out what is the prepotential and what is the system. So this slide is just about what is the weight lambda theta function. The weight lambda theta function basically means that these periodicity conditions, they have some lambda, this exponent here has lambda factors in it, and if lambda is 1, this is the original theta function, and if lambda is not 1, you basically have some theta functions of lambda times t. So your period matrix is a multiple of the original period matrix. And so these functions, they form a linear space, and there's a basis, like there's a couple of bases actually. And so by using one of the bases, we can rewrite it in the basis, and then the coefficients for each bracket here will have coefficients in front of these basis functions, and these coefficients form a vector. So the explicit form of these vectors, so as I said, you'll encounter some the period matrices that are multiples of the original one, and so these are the theta constants. So this is the exact theta constants that we encounter when we rewrite the Poisson commutativity conditions in terms of theta functions. Basically, what we did is we just removed the z dependence from the commutativity conditions, and now we don't have any momenta to worry about. We have just equations that only depend on the period matrix. For example, the first, as I said, for n equals 3 and 4, they're identities. This Poisson commutativity conditions are identities, and they're working for any period matrix, but starting with 5 particles, it's actually not true, and the conditions will provide us with constraints. And so to figure out the constraints, we obviously need to have some expansion, and we work in the expansion of instanton expansion, or the expansion in powers of q, which is the exponent of tau, and tau is our complexified coupling constant in the Seiberg-Witten theory. And for this particular this constant is dimensionless, and this is a UV coupling constant. So the only thing that we assume is this form of the period matrix, that it starts with tau, and there is a perturbative part, and there is some infinite expansion in k. So we'll be just using the perturbative expansions like this. We'll have q small ij, which is just the logarithm. This is just like fij to the power of -2 perturbative contribution, and some instanton corrections in powers of q. So qij and q without lower indices, they're different. Q without indices is just like exponent of tau, and q with lower indices is our unknown functions. So, and also we should the coefficients, the constant coefficients, basically the third derivatives of the prepotential, they're also expanded in powers of q, and so we can perturbatively, order by order, rewrite our conditions. And our conditions were some vectors with linear with constant coefficients summed up. And basically, this is just a linear system with some matrix L and vector, small vector P in the leading order. And this linear system, for this linear system to have solutions, we should have the determinant of the L matrix to be 0. And in this case, if we write it explicitly, it's some big, some huge matrix, but you can actually easily, more or less easily determine the family of solutions. And the family of solutions is that the most general solution is the perturbative part of the prepotential that corresponds to double-elliptic system. And if you take the limits, trigonometric limits of this expression, you'll have like the sine and the trigonometric here, the trigonometric functions or hyperbolic sine here, and the rational, just the differences.
With L, it looks like a Sylvester matrix for two polynomials, right? It's is it?
Yeah, I'm not sure. This was some time ago, and we just got it, and yeah, we didn't think much about it, but yeah, maybe there is some interesting parallels, but yeah, we just worked with it to figure out what is the general solution. We just assumed to work with it, we assumed that Qij's are some Taylor expansions and differences of AI minus Aj, and this constraint provides recurrence relations for the coefficients in the Taylor expansions, and then you can figure out what is the most general function, and the most general turns out to be this elliptic function. And as you can see, we're working, this is the leading order in the first elliptic parameter, which is the complexified coupling constant tau. And if you take tau hat to infinity, and then you're actually working with Calogero, with a system dual to elliptic Calogero. But since we're talking about Dell, we have second elliptic parameter, which is this parameter in this elliptic function here. So that's here we recover the second elliptic parameter as a solution to this constraint. But this approach is not very easy to use, because obviously we have some very huge, these vectors are pretty big vectors, and it's hard to even compute the perturbative part, which is known. So to compute instanton corrections from these constraints are probably possible, but hard. So this just shows that these constraints are actually work, and the hypothesis has the grounds to be true. So next, what we can do with the same basic equations is that we can view this the commutativity conditions as actually equations of the prepotential. So we don't want to forget about the prepotential. We want to remember that pi ijk is actually the third derivative of the prepotential, and you're summing up the same vectors. So C alpha ijk are the same vectors defined here, and now you're summing up those vectors with the third derivatives of the prepotential. And again, you can use these Q expansions or instanton expansions for the period matrix and for the third derivative of the prepotential. And you can use this to compute perturbative and instanton part for any n greater than 2. Oh no, I think greater or equal to 2. That's a mistake. N equals 2 is included. No, sorry, no. Greater than 2, because for n equals 2, there's one Hamiltonian, and the second one is the sum of all momenta. It's P1 plus P2. So there are no commutativity conditions. This says the commutativity between the one Hamiltonian and the overall momenta is trivial. So yeah, this works for any n greater than 2, and we can look at free particle example. And this equations here, basically what happens in any n, this equation is just for the sum for any n, sum runs from 1 to n, and this is some exponent of the second derivative of perturbative part of the prepotential times the third derivative perturbative part. And combining all these equations, we arrive at the same results we arrived earlier for the constraints. But this is actually, you don't need to wait for 5 particles. You can already do this for 3 particles and arrive at the same result. Solutions to these equations are actually double-elliptic or 6D prepotential with matter in the joint representation. So yes, so computing. So what you are able to compute the prepotential and also compute the instanton corrections, and this allows one to generalize and to actually write down the general form of the prepotential. So obviously, the general form for the 4D prepotential, which corresponds to elliptic Calogero system, is known, and you can obviously recover it as a limit from here. So this form is more or less obvious, except that what is not obvious about this form is that the coefficients in these expansions are only functions of Eisenstein series. So this part here, the perturbative part, was known and is known, and that it is some elliptic functions. Sigma is the second derivative of this logarithm here. So basically everything written in terms of the same things. And when you take the second derivative, this logarithm of the prepotential, this logarithm becomes basically 1 over sigma squared. So in the period matrix, everything is written in with the help of the same functions of A's, this 1 over sigma squared function. So the non-trivial part is that these coefficients in the expansions depend on both elliptic parameters only through the Eisenstein series, and this is just the Eisenstein series here. And the important thing here to notice is that E4 and E6 are modular forms, but E2 is a quasi-modular form, which means that under the modular transformation of tau, when tau goes to minus 1 over tau, E2 acquires a shift, which is tau dependent, and so this is not a what is called so these coefficients are not modular forms; they're quasi-modular forms because of the E2. So, for example, we can expand further these coefficients in powers of the mass. Epsilon is the mass, and it could be m, but it's epsilon for the reasons because we had to change the parameters. There's obviously you can rewrite mass as some function of epsilon, and then there will be just different expansions. But yes, we're just using epsilon as a notation for the mass here. And so if you expand these coefficients in powers of the mass, you will have this Eisenstein series coefficients, and in the second parameter, for example, and you'll be multiplying them by the quasi-modular forms in the first modular parameter, and vice versa. So your answer is actually could be written fully in terms of Eisenstein series, but there will be two types. One type is a function of the first modular the first tau, and the second type is E hat. So-called E hat is the quasi-modular form of the second tau hat. And yes, and the weight is fixed by the power of but the power of the mass, and 1 over sigma, the powers of 1 over sigma function. And so, Peter, you're asking about explicitly, you're saying the while symmetries?
I was just worried about the A's, right? Yeah.
Yeah. So, what I'm saying here is that all the indices in C's are symmetric. So like they're symmetric under permutation because we just this formula explicitly just created to have all the symmetries. So these coefficients are symmetric under permutation of indices, and we also have only this the an-1 root system, which is also, you have only differences between different ai minus aj. So this is pretty heavy formula, but what's interesting about it is that we can use it to understand the modular properties. And so this is the difference between there was the difference at least between this approach and the approach of Braden and Hollowood, is that here we think of the curve, since we have n by n period matrix, we think of the curve as a genus n curve, and actually this is a n sheet covering of the torus. So we have the base torus with cycles A and B, and we have n sheets on top of this torus, and each cut is supposed to be exactly on top of the cut on the base torus. And so we can think what should happen with the curve when we look at the modular transformations of the first parameter. And the modular transformation of the first parameter, we know what they do to the base cycles. So yeah, I need both. I cannot put the picture and all the formulas on the say, so I need both. So the first transformation is trivial. It almost does nothing, and it shifts the period matrix by the identity matrix. This is completely harmless transformation. Nothing else needs to change, and the period matrix just shifts by the identity. However, when we consider the second generator of SL2Z, tau goes to minus 1 over tau. The cycles on the base torus, they change. And as you know, by the definition of the A and A dual, A is the integral over A cycle, and A dual is the integral over B cycle, AI cycle and BI cycle. But since we know that AIs and BIs are exactly on top of the base torus cycles, obviously A and A dual, they need to flip with the appropriate sign. So this is immediately follows from the picture that A should go to A dual and A dual should go to minus A. And at the same time, the period matrix is the second derivative of the prepotential, or in other words, it's the derivative of A dual with respect to A. And when A dual and A interchange with the minus sign, obviously this matrix should go to minus the inverse matrix. So this is a pretty important property, that just by, if we have the period matrix as a function of flat moduli and parameters tau and tau hat, under shifting or under the second modular transformation, the whole matrix should go to minus the inverse. And this is what I was talking. This is what I made a comment to the yesterday's Andrei's talk, that his transformation is also, maybe he didn't have the minus, but his transformation was also when he was changing h bar to -1 over h bar, his matrix, which was, I believe, that transformation matrix between different bases. right?
But each bar in his talk is not what I mean. It's epsilon. It's epsilon in yours. So
yeah. But this still and there was some like A's and something else they interchange. So there is some interesting similarities, because this is pretty this property is actually true not only for elliptic systems, but also you have this modular properties for any like curve. You have modular anomaly equations for for curves that correspond to theories of fundamental matter. You just need to work harder to find the proper parameters. Here we have this tau, which is explicit, and we know. And there, for other curves, these parameters are some complicated functions of A's. Yeah, so that's the modular anomaly equations for theories for spectral curve corresponding to theories of matter. They also present, but a bit harder to write down. So we figured out this transformation for the period matrix, and then we can basically work with our representation that we wrote down in each order in epsilon, and we can figure out when this transformation takes place, what should happen to other parameters, because we only talk about tau and A goes to a dual, but we also need to change all other parameters in order for this transformation to work. And so what we figured out that the transformation is pretty simple, actually. The only non-trivial transformation is that when we consider the inversion of the second modular transformation, the first elliptic parameter, the second should shift. And the shift is not even in general, is not even a integer. So we'll talk about a bit later what does it mean for the duality group. So we figure out that this is what the full transformation, this is how the full transformation work. If you substitute all these shifts into the period matrix will go to the minus inverse of itself. And so this can be pretty simply, if you write down the formulas and integrate a couple of times, it's because E4 and E6, and remember I wrote everything can be written in terms of E2, E4, and E6. And E4 and E6, they just scale when you do this transformation. They just, E4 drops out tau to the fourth, and E6 drops out, no, tau to the second, probably, or tau to the fourth. I already forgot. So E4 and E6, they drop out just the multiple of tau when you do the transformation. But second Eisenstein series, it gives a shift. And so this means if you just expand this transformation, if you write it down and you expand it up to the first order, you'll see that you're just getting the partial derivative with respect to second Eisenstein series. And so, and because you also have shift in the second elliptic parameter, you'll also have the partial derivative with respect to the second elliptic parameter. So this is this first modular anomaly equation. And the interesting thing is that it's different from the four-dimensional one, or from the modular anomaly equation for the elliptical algebra, because in the elliptical algebra there is no tau head dependence, so you just drop this second partial derivative. And the same thing for the Rugenar's case. It's the 5D theory. There is also no there's no this term. There is no when I say there is no second term on the left hand side, I mean that the modular anomaly just works with just partial derivative of E2 respect, which depends on the first tau, and so you don't need this second term. So the same can be the second modular anomaly equation is even simpler, because this transformation doesn't mix perturbative part and instanton parts, because this transformation actually mixes them, and you need to work harder to figure everything out. Here, the modular transformations of the second second tau, tau hat, they don't mix perturbative and instanton. So just looking at the sum of classical and perturbative parts, we can figure out the transformations. And we see that the transformation is covariant. When the second tau goes to -1/tau, we get a shift in the first tau. And so the second modular anomaly equation is the left-hand side is the same. We just replace tau with tau hat, but the right-hand side is just the sum of AI square, which you can put to 0. Here we just keep the sum of AI is non-zero. Just this is just this is related to some classic. This is up to redefinition of the classical part of the prepotential. So this is not very essential, the right-hand side. So to summarize, the modular properties is that it's the duality group under these two transformations of two parameters. It's not actually the direct product of two SL2Z. Instead, we have 4 generators, and the shift is actually not even an integral in the general case. And so this is something to think about, and maybe this is a indicator that we need to embed our curves somewhere, and then it's going to look easier. So now it looks like it's something is so we are using a representation that a bit complicates stuff, but still it's not a very, from the computational point of view, it's not a very big complexification. It's just a shift, and it's not, there's no theta constants, and I think the shift is just purely depends on number of particles, the mass, and the other
so they depend on one continuous parameter, right? So n epsilon squared.
Yes, and p. And I mean, they like somehow, this transformations rule, they imply you can also write tau as, since a is actually a function of tau, right? When we say a goes to a dual, a can be written as some function of tau 2 with some other. You need to replace a with like coordinates or whatever, and that are not changing. So all these arrows means that actually tau hat is, they're somehow dependent on each other or something, right?
It's clear
they're not completely.
It's some non-trivial subgroup of, but it's not a subgroup of the product, right? It's something else. It's a group that doesn't have a name, I guess, right?
Yeah, but what I'm saying is just from functional point of view, this transformations law, like when we say that a goes to a dual, this means that a is actually a function of tau. You can actually write a as a function of tau, and this is what we're saying, that a is an action variable. It actually depends on tau, although we are writing it as a independent variable in the expansion here, like in this formula or in any formula. You have a here and you have taus here, but if you think about it, a is also a function of tau because it changes when tau changes. So yeah, so this is the simpler takeaway from the whole point of view, is that eventually we can, and I didn't have time to talk about it, but using, as in the 4D case, this modular anomaly equations allow you to compute the prepotential again. You can use them, but you need to add, since there's partial derivatives, you're losing some information. So if you have like the ring of quasi-modular forms, all the polynomials are some, you'll have e2 to the 3, yes, you have some polynomials in e2, e4, and e6, And when you take the derivative with respect to E2, you lose some information. You lose some terms that, like, for example, E4 times E6. When you take this derivative, you lose the information. So to recover it for some lower number of particles, for n equals 3 and I think n equals 4, you can use what was in 4D case. This was a pure gauge limit to the Toda system. This was the limit where you take the mass to infinity by simultaneously sending q to 0. Q is the instant parameter. So here there is also a limit here, but you cannot send mass to infinity because this epsilon parameter is actually lives on the torus. But there is a singular point in this sigma function here, and you can send mass to this singular point and ask for and basically do the same. You send epsilon to the singular point, and at the same time you're sending the q to 0, so that the product is finite, and then this gives you enough information, at least for some for n equals, for some particular finite number of particles, to compute the whole prepotential. So this is also can be useful. And furthermore, you can generalize this modular anomaly equations to Nekrasov partition functions. And you actually don't need them to compute the full Nekrasov, but since sometimes you need the quantum co-limit of Nekrasov partition function, sometimes the modular anomaly equations could be helpful and easier to compute. It could be easier to compute this limit with the help of modular anomaly equations than just from the limit of Nekrasov partition function. Okay, thank you. I think that's it. Almost, I mean, on time.
Okay, thank you very much, Gleb. Please, questions?
Thank you. Yeah, and the interesting the developments recently is that Peter and Shamil, they computed quantum Hamiltonians that are easier to work with, and so people are already introducing generalization of McDonald polynomials that are wave functions for this eigenfunctions for these Hamiltonians, and they also have the conjectures about. So when you have quantum Hamiltonians and eigenfunctions, you can work out the PQ duality again, and they have the suggestions for different eigenfunctions, and so this could really help to understand the connections between these Hamiltonians that are particularly complicated with this simpler but very more useful Hamiltonians by Braden and Hollowood and Peter and Shamil.
Yeah, Zienkiewicz will talk about that tomorrow more. So
yeah,
looking forward to his presentation.
Yeah, this is interesting developments, and this from this point of view, you can imagine this as being some kind of you instead of this identities I was talking about or constraints, maybe there would be some statement that on this particular period matrices, the higher genus theta function factorizes to something simpler, and this statement is in itself is a pretty interesting statement about prepotentials and about period matrix, which we are working with, because today we had this complicated constraints, but maybe if we figure out the transformation between different Hamiltonians, we'll see something easier. Yeah.
Great, thanks. Any more questions? Well, I guess it's getting pretty late on the East Coast, right? And also here. So yeah, so then we conclude the session, and we'll meet tomorrow again at 9 a.m. Eastern, 9 a.m. Pacific, p.m. Pacific for 3 more talks. Thank you, everyone. See you tomorrow. Bye.
Thank you very much. Bye.